If you're a researcher working with sensor data, you know the drill. You have a burning scientific question. Maybe it's about local air quality impacts on respiratory health, or detecting aftershock patterns in seismic data. But before you can answer it, you're drowning in infrastructure. You're wrestling with workflow management systems, container orchestration, provisioning edge nodes, and debugging distributed runtime failures. We call this the blank page bottleneck. Scientists often spend more time on execution mechanics than on actually exploring and analyzing their data. A new paper from researchers at the Renaissance Computing Institute and USC tackles this head-on. They propose a pattern-based, AI-assisted methodology that shifts workflow construction from code-first to intent-first design. Using Pegasus workflows on the Fabric testbed, they demonstrate a development loop that compresses multi-stage workflow development from weeks down to just days, even for novice users. And they do it while preserving the rigor, portability, and fault tolerance that scientific computing demands. Let's break down how this works, the deep technical details of their approach, and why this synergy between LLMs and workflow engines is a game-changer for edge-to-core computing. So how does this actually function? The core idea is pattern-based engineering, grounded by AI. The researchers identified 4 design principles: intent-first development, pattern reuse, separation of concerns, and human-in-the-loop assistance. This results in a 5-step development loop. Step 1 describes science. You define your data sources, analysis steps, and outputs in plain English. Step 2, ground with context. You provide an AI assistant with a proven, existing Pegasus workflow as a structural template. This is crucial. Grounding the AI in validated patterns prevents hallucinations and ensures the generated code follows established best practices. Step 3, generate skeleton. The AI produces an executable Python code with task definitions, I/O declarations, and dependency graphs. Step 4, refine. You, the human, guide the iteration to adjust resource requirements, containerization, and parallelization. Step 5, scale. You deploy to edge, clusters, or clouds without redesigning the workflow, using Pegasus catalogs and HTCondor placement policies. Now, why Pegasus? Directed acyclic graphs, or DAGs, are explicit, readable, composable, and execution agnostic. They map perfectly to how LLMs reason about structure. Plus, Pegasus has been open source with extensive documentation for over 20 years, making it work out of the box with commercial LLMs. For edge-to-cloud workflows, HTCondor class adds steer tasks to appropriate nodes. Infrastructure is provisioned programmatically using FOB-lib on the Fabric testbed, with typical deployments including a submit node hosting Pegasus and HTCondor, edge workers near data sources, and cloud workers for compute-intensive stages. To prove this, the team ran through a chain of case studies that demonstrate progressive workflow reuse. They started with the Orcasound hydrophone workflow as the baseline pattern. This implemented a canonical sensor-driven structure: ingest, preprocess, transform, infer, aggregate. It ingests audio segments, converts them into analysis-ready formats, performs ML inference to detect orca vocalizations, and aggregates predictions across sensors and time windows. Because of its explicit dependency graph and containerized transformations, it was ideal for adaptation. From there, they built an air quality workflow. This was incremental. They started with a baseline ingest analyze detect pipeline using OpenAQ data, which took about 3 to 4 AI prompts. Then they extended it to LSTM-based ML forecasting, adding another 3 to 4 prompts. Finally, they integrated Sage sensor network data with 2 to 3 more prompts. Each extension preserved the upstream logic. Early executions hit realistic runtime errors, like missing API credentials inside containers causing HTCondor jobs to enter a held state. But because the structure was grounded, AI-assisted log analysis across the Pegasus, HTCondor, and container layers made diagnosing these issues straightforward. Next, they reused the air quality pipeline to build earthquake and soil moisture workflows. The earthquake workflow swapped ingestion for USGS seismic feeds and introduced conditional branching to trigger aftershock analysis and hazard assessment for high-magnitude events. The soil moisture workflow adapted ingestion for in-situ soil sensors and weather data, followed by feature joining and regression-based prediction. In both cases, the underlying execution model and deployment configuration remained largely unchanged. Here's where it gets really interesting for edge computing enthusiasts. The researchers extended these workflows to heterogeneous edge resources without modifying the abstract workflow logic. For the soil moisture workflow, they offloaded I/O-intensive preprocessing stages to BlueField 3 data processing units, or DPUs, via Pegasus site mappings. This allowed them to experiment with alternative placements along the edge-to-cloud continuum. They also configured a Raspberry Pi as an edge participant for data ingestion and lightweight preprocessing, with downstream analytics executing on cloud resources. The key technical insight here is that heterogeneous edge devices can become first-class participants in end-to-end Pegasus workflows using standard scheduling mechanisms. There's no need for bespoke edge orchestration layers. HTCondor class adds steer tasks to appropriate nodes. For example, class adds can direct specific tasks to DPU-enabled edge workers versus CPU-only cloud workers, all based on the workflow's requirements and the infrastructure's capabilities. Let's look at the numbers. The evaluation focused on user productivity, from the perspective of a novice Pegasus user. This user had only completed a single tutorial before starting. They used Claude Opus 4.5 as the primary AI assistant, supplemented by ChatGPT and Gemini for debugging. The results were striking. A runnable workflow was generated within 3 to 4 prompts when grounded in an existing pattern. The total development effort across all 4 workflows was approximately 4 to 5 days, or about 8 to 12 hours per workflow. Compare that to the weeks it would take a novice to learn workflow abstractions, configure environments, and diagnose distributed failures manually. They also observed compounding productivity gains. As they moved from air quality to earthquake and soil moisture, the iteration cost decreased. Later workflows required fewer execution attempts because of inherited configurations and prior debugging experience. Interestingly, the majority of the iteration effort wasn't spent correcting workflow logic. It was spent resolving execution time configuration issues, like credential propagation, data staging, and container runtime problems. This highlights that AI is incredibly effective for structure generation, but the human in the loop remains essential for the gritty details of distributed systems debugging. In conclusion, this work demonstrates a powerful synergy between pattern-based workflow engineering and AI-assisted development. By grounding LLMs in validated Pegasus patterns, the researchers showed that scientists can rapidly adapt sensor-driven applications across domains and execution environments, from cloud to blue, field 3 DPUs and Raspberry Pis, without redesigning the core workflow. The methodology preserves rigor while dramatically reducing the time to insight. The limitations include a focus on development effort rather than application performance, and reliance on a single user's experience. Future work looks at team-based evaluations, longer-lived workflows, incorporating execution feedback for automated adaptation, and integrating AI agents that proactively suggest optimizations and placement strategies. For those interested in diving deeper, this research was supported by the National Science Foundation, and the workflows are available on GitHub. If you're working at the intersection of AI, scientific workflows, and edge computing, this pattern-based approach is worth exploring. It's a practical step toward democratizing complex distributed application development. Thanks for watching, and keep pushing the boundaries of what's possible with sensor-driven science.